So come to the third part of the three-part video on call option pricing. Okay, this is the third part of the three-part video. So you can find the other rest of the videos at www.hour.com. And this on call option. The first part I have explained what is a call option, and the second part I have explained how to prove this equals to this, and then in this third part of the video I'm going to prove the rest of the equations related to the call option Black-Scholes call option pricing formula. So okay, for this thing, when we differentiate the d1 which is the d1 as stated here, when we differentiate the d1 respect to s0, it will be equals to, when we differentiate d2 with respect to s0. This is what we are going to trying to prove. And because we know that d1 is, again, the d1 is equals to right here we see d1 is equals to d2 plus sigma root t. So I just bring over basic algebra, I just bring over, so my d1 would be equals to d2 plus sigma root t. Okay, so then that's why when we come to here, I just change d1 to d2 plus sigma root t. And when we differentiate with respect to s0, all these other expression sigma and root and the t would be, we treat them as fixed. So when we differentiate with respect to s0, this thing just becomes 0. So ds0 sigma root t is just 0. But when we differentiate s0, then with d2 is a variable dependent on is a function of s0, so it should remain. So that's how I prove that differentiating d1 respect to s0 is same as differentiating d2 with respect to s0 will give you the same. So in the part 2b of the tutorial, okay, we are it means the tutorial given by the course on financial maths. Okay, so this Black-Scholes price formula, I was supposed to find dc not over ds not. Okay, so we are supposed to differentiate this with respect to s0. So we will differentiate implicitly. So that means differentiate this with respect to s0. That's what we get for here. And when we differentiate this term with respect to s0, this part, okay, this part we will differentiate using the chain rule. So the chain rule of the differentiation, so you can Google if you to find out what's the chain rule. So basically I'm differentiating this function m prime and keeping inside the input, keeping input inside, and then after that while I differentiate the whatever is inside this bracket with respect to s0 as the chain rule. So actually because all this part and the d1 both contain s0 as a part of the variable, because you see the d1 contains the s0 as d1 is a function of s0, so it will not goes to 0 when you differentiate it. Instead it will just remain as remain there, right? So then no, not this page, so here, so it will just remain here. So we'll keep this, differentiate this part, we'll get this is just the product rule, and then we'll keep the other nd1 product rule of differentiation. So we keep the nd1 and then we differentiate s0. When differentiate s0 with respect to s0, we just get 1, so we cancel it off and replace with 1 times nd1 still nd1. So after that minus, okay, this part we treat it as just a constant, okay, because these are not functions of s0. Okay, so then when we differentiate this part, we use the chain rule again and we get this. Alright, and then using equation 11, okay, using equation 11 we know that differentiating d1 with respect to s0 is the same as differentiating d2 with respect to s0. So therefore I change this d2 from here to here. I keep everything from this equation to this equation over here. I keep basically everything except I change this ds not d2 to ds naught d1. Okay, so because they are equal by equation 11, they are equal. So then the next thing that I do is I just factorize out. So because there's these two terms are the same, so I just factorize it out, and I keep this part, I just come to here, and this part will just come to here. So this is basic factorization, and this nd1 I bring over to the other side. So to this part. So then because in equation 10 earlier, in the earlier tutorial, we have proved that s naught m prime d1 equals to ke minus rt n prime d2. This is the same as saying s naught m prime d1 minus ke minus rt m prime d2 equals to 0. Okay, and this thing you realize is just this, they are the same. So this part, since that is equals to this formula is equals to 0, right? And this is, so this is equals to 0, so it changes 0 0 multiplied to anything is just 0, so I'm left with nd1. So this is how we show what we find this one. Okay, so the answer to this question is this nd1. All right, and come to the next part. We are asked to prove that let's say if we differentiate the call price of the call option by sigma, the volatility the volatility of the share price. Okay, so and we differentiate this, we are asked to show that they are equal, and indeed we are able to show that using again just the chain rule, and we find that, yep. Okay, so keep this, for this part I'm keeping s naught, okay, and differentiate this m prime d1 with respect to sigma. Now s naught is just when differentiating respect to the volatility sigma, s naught is not a function of sigma, so you just treat it as a constant, so like fixed. So then m prime, when differentiate this thing, we just use the chain rule. Okay, the differentiate this function, and then keep the inside, and then differentiate the inside, which is the chain rule. So then after that, minus ke minus rt, I'll keep it because this is not all these terms are not the function of, they are not functions of the sigma, so you just treat it as a constant. And then again, when I differentiate this with respect to sigma, and differentiate, this is this function, and so this is still the chain rule. Okay, then we will stop for this one here. We'll not simplify the expression further because it's not necessary, and just differentiate the price of the put option with respect to sigma. So the put option price sync model is this. Okay, you can Google for the put option Black-Scholes put option pricing model, and then you get this formula, and just need to differentiate this and then get the using chain rule as well, and chain rule as well. So same thing as earlier. So then we know that the probability distribution function for the normal distribution is just this formula, and then when we replace minus x with minus x, we still give us the same thing, because the square minus x square is just x square, and then there's a minus in front. So then that means this and this are, the two are equal. So that means the m prime d1, if I replace inside with d1, and this minus d1 will also be equal. So if they are equal, then that means that when I follow from here, let's say this, I just minus d2 would be the same as n prime minus d2 would be the same as m prime d2. That these two would be the same, they are because of this formula. So then here we have ke minus, so differentiate this thing, we are just skipping everything else. So then this minus d1 I change to d1, okay, also because of this formula here, so then the rest I'll keep it the same. Then differentiation, and we know that when you differentiate, when there's a negative sign in front of the function that we are differentiating, we can actually bring the negative sign to out of the out of it. So same, therefore I'm trying to bring in the next step, I bring the minus here to the front, and the minus disappear from here, and here the minus here I also bring to the front, and minus multiplied to a negative, so it becomes a plus over here, and the minus here disappear. So, and therefore we arrive at this for the d over d sigma p naught, and we realize this is just exactly the same. Comparing this to the equation 13 and equation 12, we realize compare the right hand side, we realize the expressions, this expression is exactly the same as this expression, which means that this is the same as this, right? So then we are done with this 3-part tutorial. You can find the other 2 parts of the tutorial at www.owlowl.com under maths video links, and under financial mathematics. Okay. Okay, thank you. Then that's all for this tutorial.